Hello, everyone, and thank you for attending to my talk. I'd like to talk about the unreasonable effectiveness of deep learning, about what deep learning is, why is it so good, why is it so effective, what has it done for us, and what will it do for us in the future, what should we expect. And so with this context, let's begin. And let's begin by introducing the hero of our story, the artificial neuron. Many years ago, computer scientists were thinking about how the brain works. They were trying to understand how these very complex biological neurons could be operating so that when you make brains out of them, you get smart behavior. Now, biological neurons are very complex, but scientists conjectured in the 40s, McCulloch and Pitts, they conjectured that maybe the thing that's important about the biological neuron is a very simple function that's described by an artificial neuron on the left. It's a conjecture, it's probably not true, but it's a very inspiring conjecture. Because while biological neurons are very complex and difficult to understand, the artificial neuron, by comparison, is extremely simple. Now, of course, biological neural networks, brains, are even more complex. They're even more difficult to understand. And despite lots of research in neuroscience, our understanding of biological neural networks is rudimentary. In contrast, artificial neural networks, while they can also be quite complicated, at least we know how to mathematically train them. We have a mathematical learning rule that allows our artificial neural networks to learn from experience in an easy to understand way. We can understand the learning of neural networks precisely enough so that we can implement it on a computer. And therefore, get neural networks to do interesting and useful things. So all this work, all this research into neural networks has eventually produced a simple set of unbelievably, like a very small, very simple set of principles, which is truly unbelievably powerful. Now I'll explain to you right here what this principle is in one slide. The principle is this: if you have a very large neural network and you train it on a large data set with lots of compute, then you can do amazing things reliably and predictably. And this one simple idea lies at the core of nearly all advances in AI that have taken place over the past decade since the start of the deep learning revolution. And like I would say, one thing which I find very satisfying about this is that if you compare the core idea of deep learning to the core idea of other sciences, maybe like physics, they appear to be quite complicated and you need to do a lot of study to even understand them. While the core principles of deep learning are really truly simple and they can be explained to a school child. So next, we'll go into a little bit of detail on how to use this magical deep learning formula. And the big picture is you need to choose a network architecture, which is actually going to be easy, as we shall see. You need to choose a data set, a data source. That may be a little bit harder. And you need to choose an objective to optimize how to use this data, and that will be easy again. And now I'll go over, like in what follows, I will go over examples of different famous neural networks. And we'll see how each of these choices was made in each of these examples. So let's do it. Let's begin. So the first neural network I'd like to present is Alexnet. And in this case, we've used, for the architecture, a convolutional neural network. For the dataset, we used ImageNet. And for the objective, we used the objective of predicting the label. That is all. was a relatively large convolutional neural network trained on a relatively large data set, and that gave us the result. We shall then proceed to our next example, the sequence-to-sequence architecture. So this was a neural network, which was the first neural network that really showed that neural networks can do really good machine translation. And there the architecture was the long short-term memory, the LSTM. It's just a kind of a recurrent neural network. You don't even need to know what it is for the purpose of this presentation. Just some architecture which is good at taking a sequence as an input and producing a sequence as an output. The dataset was WMT, which was just a translation dataset. It had sentences in English and sentences in French. And the goal of the neural network was to predict every word in the translation. And again, the neural network was a little bit large by the standard of when this work was done in 2014. And it performed really well. It was able to outperform the classical translation systems. But then we continue to a different kind of a neural network. Now, this is a neural network that's based on reinforcement learning. This is also an LSTM, just as before, the architecture. But the dataset is no longer a static dataset like what we've had previously. It is now a reinforcement learning environment. And in this reinforcement learning environment, the neural network would play games against a copy of itself to create training data. And the goal was to predict the actions which lead to more success than usual. So the dataset was generated on the fly, but the principle is still very similar. You have a large neural network trained on a large dataset, and you get very strong results. And in the case of OpenAI 5, we've been able to train a neural network to beat the world champions at this game. And just for a little bit of context, because I realized that perhaps not everyone will know what Dota 2, the game of Dota 2 is. So it's a real-time strategy game. A real-time strategy game means that you've got a few characters on the screen and you control them and you tell them what to do, and then they do it. And it's like this. It's a team of 5 players against 5 players, and each controls its own characters, and the characters go into various battles essentially. And the professionals in this game are really good, and they dedicate their life to it. And it was a very large professional scene with lots of money in it. And so this approach was able, this simple approach, we just trained this LSTM, this large LSTM, on the data generated by the Dota environment, was able to beat the world champion at this game. Oops. So the next example we'd like to go is solving a Rubik's Cube with a robot hand. This is a very similar example to the previous example with Dota 2, where once again we have an LSTM which controls the policy. We have a data set which is a simulated, in this case, the data set is a simulated robot hand, a real environment. And again, the data was generated by interaction with the reinforcement learning environment. I'm not elaborating exactly on how this step is done, although it is also quite, it's not like a super sophisticated thing at all. And the goal, as before, is to predict the better action, predict the action that led to the unexpectedly good result. And we were able to then do sim-to-real transfer and actually solve the Rubik's Cube on a physical robot. And yeah, that's the formula, and it just keeps on delivering all the time. The next example I want to present to you is CLIP. So CLIP is an interesting neural network because this time we have the transformer, the vision transformer. We see it first. Actually, sorry, I think I'm gonna skip the slide. Yeah, okay. It jumped. So now I want to tell you about GPT-3. So GPT-3 is basically the same approach. We have a neural network, in this case, a transformer, and it's trained on a large data set, which is text on the internet, with the objective of predicting the next word in the text. The thing that makes this, the discovery of GPT-3 is really the realization that predicting the next word in text is a very interesting objective. In other words, that if you have a neural network that is really, really good at predicting text from the internet, then it can do a lot of different things, and it can achieve a great deal of competence in a large number of language tasks. And for an analogy, if you can guess the next word, if you can have a good enough educated guess about the next word in text, then it means that you must understand the text at least somewhat well. And to give an example, suppose you're reading a mystery book, a mystery novel, and at the end of the novel, the detective is about to reveal the identity of the criminal. If you can guess, like you can narrow down the list of words of the name of who could that have been, it's like this person or that person, or maybe you narrowed it down to just one person. To do this, you really need to understand the text. A neural network, which is trained to predict the next word, is doing exactly that. But the core principle on which it's all based is a neural network trained to predict text. Another neural network which is trained to predict text is CLIP. In this case, the data set is images collected from the internet, and the text is various text captions that exist around those images. And you train a convolutional neural network in this way. In this case, actually, it was a vision transformer. When you train a neural network on this task, on this broad set of images and text captions that are associated with it, when you do that, then the neural network learns general visual capabilities, and it develops the ability to perform a huge variety of vision tasks, zero shot. So if you have any vision data set, you just take this neural network and you get a very robust and reliable results out of the box. And this is very important. I want to spend 1 minute explaining this point. There is something very, so if you go deep into the details of deep learning and of how people run their metrics and evaluation, you'll notice something very strange. You'll notice that very often people report that they achieve human level results in a domain like vision, yet obviously vision isn't solved. How can that be? The answer is there is a very form of subtle overfitting that's going on anytime the trained data and the test data come from the same distribution. So for example, in the very famous benchmark of ImageNet, you have a training set and you have a test set, but they are from the same distribution. So if you train your neural network on the ImageNet training data, your test performance, in a sense, will be inflated, because when you take your neural network to the real world, the images will come from a different distribution, and your performance will get worse. This is not so for the CLIP neural network, because it was trained on a broad set of images from the internet, rather than one narrow task, which is how things have been commonly done up until now. Another very interesting neural network is Dali, which is basically, so CLIP is image to text, Dali is text to image. We've taken a transformer, and basically it's like a GPT-3 transformer, a little bit smaller, and we've just taken text and image pairings. We've found some way to encode images as discrete tokens, and then we used the text, essentially the text generation ability of GPT-3 to generate the language of those representations of images. And here you have an example. But it's the same next word prediction, but in the context of this language that describes images. So we literally took a smaller GPT-3 and changed the data set, and suddenly you can generate images. So this is very cool. And finally, I'll finish with Codex. Codex is, again, a smaller GPT-3, just trained on predicting the next word in GitHub. And as a result, the neural network can code quite well, and it can even write entire functions from function bodies from comments. And it follows from predicting the next word in GitHub. If you can predict the next word in a large code base really well, it also means, as a corollary, that if you read a comment which says the following function does X, your neural network will have a pretty good probability mass on the text of a function which actually does that, but only if the neural network is good enough. All right, I have a few minutes left. I'll talk to you just briefly about what we should expect in the future. Obviously, I think it's fair to say that deep learning has been progressing quite rapidly, and it is definitely a safe assumption that it will continue to do so. But in what ways exactly? So one of the things that we should expect to see are improvements in efficiency. There have been a fairly small, but very, very significant improvements in the efficiency of our architectures and also our optimizers. Starting from the recurrent neural network many years ago to the LSTM, there was a big jump, to the transformer, which was a very big jump as well. Will we have one other big jump in the future? The answer is maybe. And if we do get such a jump, then we should expect a rapid increase in all of deep learning capabilities across the board. One thing to note is that there has been a great deal of unification in deep learning. We basically use just one architecture for everything. So maybe a future architecture will also be used for everything, and it will improve all applications of deep learning and AI across the board. We should expect a unification of modalities because certainly it just seems useful. The different modalities give our neural networks a different way of looking at the same data. And by having a single neural net which is good at many modalities at the same time, it will have a deeper understanding of all the concepts that we wanted to learn. Similarly to how human beings benefit from exposure to the same concepts from multiple aspects and multiple angles. I'll also mention reasoning as an important area where we should see a lot of progress. It's fair to say that deep learning has made a lot of progress on every domain of AI, every single domain of AI, though reasoning, I feel, has been lagging behind compared to the rest of the areas where we've seen progress. Now, the two places where we've made work at OpenAI on reasoning is in the Codex model, which can actually write programs and do so quite well. But also more recently, we've made progress in formal math, and we were able to solve some math Olympiad problems, which are quite hard. We were even able to solve 2 problems from the International Math Olympiad. And those problems are not easy at all, and they require a lot of reasoning. So those are just small steps that we are taking towards making reasoning neural networks be better. Towards making neural networks be better at reasoning. And finally, I want to talk about alignment, safety, and reliability. So this is going to be, the way I'll explain it is as follows. The neural networks that we have today, they are already really good, but we still can't use them in many applications because they are not reliable. They make mistakes which are random and undesirable. They're not safe, they have toxic outputs, and they're not aligned. They don't follow our intention quite well. And here I'd like to describe the simple path towards improved alignment, safety, and reliability in the near future. In short, as we make our neural networks better and larger, they make fewer errors, and this is well established. But in addition to that, the better neural networks also fine-tune faster. And what that means is that it allows us to easily and quickly specify behavior with an approach which we developed, which is called reinforcement learning from human feedback, where you have human teachers literally say, this is good output, this is bad output, on the outputs that the neural network produces on different complicated inputs. And because the better the neural network is, the faster it learns to understand the intention of its teachers. So what are some of the things that you can do with it? Well, you can do a whole lot of things. Like one specific project that you've done was to align GPT-3 to make it so that it explicitly follows the intentions of those who use it. So we taught it to follow instructions. Like those of you who may have used GPT-3 or other language models, you know that it takes quite a bit of effort to wrangle that neural network to get it to do what you want. It has a lot of capability, but it doesn't do what you want. It's unruly. But with the instruction following fine-tuning, we were able to teach it using a relatively small amount of effort to follow the instructions. We incentivize it to follow instructions, and people who use it love it. We have all kinds of metrics that show that even small language models, which are fine-tuned in this manner, are really preferred by raters and by users, and the large ones are really, really well liked. And in fact, those instruction following models are now the default in our API. And the same approach can be used to reduce the toxicity of our neural networks and reduce undesirable outputs. So to conclude, deep learning has made really amazing, incredible progress. The ideas of deep learning are simple beyond belief. I think it's fair to say that one does not bet against deep learning. I will stop here. Thank you so much for your attention.
Thank you, Ilya. We have time for a couple of questions. So one question that came up from Dan Offer online was, in domains where we inherently don't have a lot of data and are unique or new application domains. So do you see deep learning making contribution through transfer learning? Do you see specifically design networks that can learn with small data, or do you think that this is simply not the right place to apply deep learning?
So definitely domains we don't have a lot of data. So data is the fuel of deep learning, as well alongside compute. So maybe if data, data is the fuel of deep learning. And so if you don't have a lot of data, that does make it impossible to produce the kind of incredible progress that you see in domains with a lot of data. So when you have a lot of data, progress is actually incredible. When you don't have data, you have to do some tricks. What are the tricks you can do? Well, transfer learning is a very good first bet. Transfer learning will give you a very strong baseline. And in fact, it's probably going to be much better than any other approach that one could take today. Designing specialized network architecture, I mean, one can try to do it. I wouldn't say that this approach has a very strong track record.
Okay, thank you. And another question is, so we see the computing requirements constantly increasing for deep learning. Do you see this as a trend that's going to continue, or do you see in the future more computationally efficient networks or shrinking of computing requirements?
Yeah. My expectation on the compute requirements is that we should see two things simultaneously. On the one hand, there is a giant incentive to reduce the cost, the amount of compute that you need to reach a certain level of performance. So there's a lot of research done by the entire community to increase the efficiency of our neural networks, to increase the efficiency of our methods. So you could get the same results with less compute or better results with more compute. The other thing that, at the same time, it is also true that there will be demand for really great results, really great performance, really, really good performance. And at the highest end, even if you have really efficient architectures and really efficient methods, you will still want to use a lot of compute.
So the more computing power we're going to have, someone will find a use for it, you're saying. There's no doubt about that.
That seems like a safe bet, yes.
Okay, so on this optimistic note, thank you very much, Ilya.